The Rational Roots Theorem and Finding Roots. We're at 11.4a. If you've missed any of the previous videos, we got 8. Just click on the description. If a polynomial has integer coefficients, there's a procedure for finding all the rational roots. It's the Rational Roots Theorem. So the explanation of this, if you've never seen this before, all it means is our exponent is going down in descending order. So it goes from n to n minus 1, n minus 2, just like if we had 5, 5 minus 1, 5 minus 2, to have descending order. And the subscripts do the same thing. See that? Until you get to an exponent of 1. So we're going to let this polynomial p of x equal this descending order expression. And the first one is going to be the leading coefficient here, and this last one is going to be the constant. That's where all the coefficients are integers, positive or negative numbers. So consider a rational number denoted by the quotient of c and d to be a root of p of x, where c and d are relatively prime. Now for the quotient of c and d to be a root of p of x, c must be a factor of a to the sub 0, that constant, and d must be a factor of this leading coefficient, a to the sub n. See? So you can look at it this way. It's saying that we have to do division. So the factor of a sub 0, this right here, divided by this a sub n. That's going to give us our possible roots. So it'd be the factor of c divided by the factor of d, according to this theorem, or just look at it as the factor of the constant divided by the factor of the leading coefficient to give us our possible roots. All right? So I've got quite a bit of information for you, and hopefully when I'm finished, you're going to completely understand the Rational Roots Theorem, and you'll be able to use it with confidence. So it's saying that any rational root of a polynomial is made by dividing a factor of the constant term by a factor of the lead coefficient. Now notice it doesn't say complex or irrational. It says rational root, okay? So that doesn't count for square roots and irrational numbers, okay? Unless it's a perfect square. But this is for rational roots. We can just divide, okay? And we can make a list of numbers that may be roots of a particular polynomial. We make a list of those factors. We substitute the numbers into the polynomial to see if it makes the equation true. Now remember, sometimes none of them will make it true, which tells us there's no rational roots. So if you can't find any that make a remainder 0, there's no rational roots. Don't worry about it, just write that, okay? So we can find the roots of the polynomial p of x. Now, it could be a y or an f of x. So don't worry that I have p of x here, all right? Some books would have this, some would have y, some would have f of x. It's all the same thing. This is a polynomial, so I put p of x. So we can find the roots of this polynomial. There's an invisible 1 in front of this x, isn't there? And then we've got a coefficient of a negative 3, and then we've got x to the third plus 2x squared plus 12. So here's our constant. Here's our lead coefficient, this 1. We have to find the factors of 12. Well, the factors of 12 are a positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 4, positive or negative 6, and the positive or negative 12. These end up all being the numerators of our possible roots. And we divide by 1, that lead coefficient, which is the only factor of 1, is 1, right? But the constant won't change if divided by 1. If we divide each of these by 1, they're going to stay the same. So there's no point in dividing by 1. We ignore the signs, the positive and negative signs, because the factors for both 1 and 12 can be positive or negative. We'll find the sign when we test the root in the function equation, all right? When we do synthetic division. So we use synthetic division to find which of the values will give us a remainder of 0. So we would do any number of these, positive or negative, and we do synthetic division into this polynomial. See? If we get a remainder of 0, then we know that it's a root. And the polynomial is of degree 4, so there could be up to 4 roots. See? There's a 4 there. All right? All right. So here's the beginning one more time. we're going to let p of x equal this polynomial here. Notice it's to the 7th degree right here. We got the lead coefficient, 6, has an x to the 7th degree. See? And our constant is a minus 20, a negative 20. So we can find the rational roots of p of x if they exist, and any other roots there may be. So the first thing we do is list all the factors of 20. All right? That's our first job. Here's all the factors of 20, positive and negative. Now, we need all the factors of 6, because we have to divide each of these factors of 20 by the factors of 6. So here they are, 1, 2, 3, and 6. So we write all our numerators. These are all our numerators, positive and negative, and here's all of our denominators. So we don't need to divide by the 1, right? Because we know it's going to make it stay the same, but we need to do 2, 3, and 6. So here's all the 2 denominators, all the 3 denominators, and all the 6 denominators. Now what's going to happen is we're going to end up with things like 1/3 and 2/6. Well, that's the same thing, right? And 2/3 and 4/6, that's the same thing. 5/3 and 10/6, that's an equivalent fraction. So is that one. So we simplify the fractions and remove copies of already listed values. And then we try each remaining value in a systematic manner. So we don't need to do this one, or this one, or this one, or this one, and we look for any other copies there might be. I might have even missed one, who knows. But we know, because that this is a polynomial to the degree 7, that 7 of these roots, 7 of these factors can be roots of the polynomial. And we use synthetic division to find up to 7 of them. So we slowly take each one and do synthetic division into this polynomial to try to find a remainder of 0, all right? So now you should understand the starting of the rational roots theorem, okay? So you take the constant, you list the factors of the lead coefficient, and then that's the numerator, the constant, and the denominator factors are the lead coefficients factors, okay? Get rid of all the copies and then start our synthetic division. So now let's do the whole thing, okay? So we're going to let p of x equal 3x to the 4th minus 11x to the 3rd plus 10x minus 4. So here's our constant, 4, and here's our lead coefficient, 3. We list all the factors of a negative 4. Got a positive and negative 1, positive and negative 2, positive and negative 4. And we list the factors of 3. It's a 1 and a 3. So here's our numerators, here's our denominators. Here's our numerators, here's our denominators. See? Here's all the denominator 1, all the denominator 3. And the polynomial is of degree 4. So we know up to 4 of these can be roots. All right? Positive or negative. We remove any copies and try the rest using synthetic division. So we've got a 1 over a 1. That's a 1, isn't it? So we've got a positive 1 and a negative 1 that we could use. So using synthetic division, let's try positive 1. So we write our polynomial without any variables. Now you notice the 0 here is because we don't have an x to the 2nd power. See that? It goes 4, 3, and it jumps to x to the 1st power. So we need to put a 0 there as a placeholder. So we're going to have a 3, a negative 11, a 0, a 10, and a negative 4. A 3, negative 11, 0, 10, negative 4. Using synthetic division with positive 1, we drop our 3 down. We do 1 times 3 is 3. We write it here. We do our addition. We get a negative 8. 1 times negative 8 is negative 8. We do our addition and get negative 8 again. 1 times negative 8, we get negative 8 again. We do our addition, we get a 2. 1 times 2 is 2. We do our addition and we get a negative 2. Uh-oh. P of 1 equals negative 2. It doesn't equal 0, so it's not a root. That has to be a 0 in order for this 1 to be a root. Okay? So, let's try negative 1. We've got our polynomial written without our variables. It's just the coefficients. We do negative 1 times the 3 that we drop down, and we get negative 3. Then we do our addition, get a negative 14. We do negative 1 times negative 14 is a positive 14. Do our addition, we get 14. Negative 1 times that is a negative 14. We do our addition, we get a negative 4. Negative 1 times negative 4 makes a positive 4. Ooh, that's perfect. It made a remainder of 0. So that's our remainder. This is our quotient. We can fill in our x values as this is the constant. This is x to the first power, x to the second power, x to the third power. So we know our quotient would be 3x to the third minus 14x squared plus 14x minus 4. See? Just remember the constants there. See? And we know that x plus 1 would be a factor. Because remember, when we solve for x, if we set this to equal 0 with principle of zero products and solve for x, x is going to equal a negative 1, and that is our root, all right? So we can use the quotient to check other possible roots. So now we're going to take this quotient to check the other possible choices that we had, okay? So we did have this polynomial. Now we've got this polynomial. So what are some of our other choices? Well, we've got a positive and negative 2. We have a positive and negative 4. We also have a positive and negative 2/3. So we're going to try doing the 2/3. So we write our quotient, the 3, negative 14, positive 14, and negative 4, right here, just the coefficients. We're going to multiply it by 2/3. We drop our 3 down. 2/3 times 3 is 6/3, which is a 2. We do our addition and get a negative 12. 2/3 times negative 12 is going to give us a negative 8. We do our addition and get a 6. 2/3 times 6 is going to get us a 4. Ooh, that's awesome. We got another 0 for a remainder, and here is our quotient. So p of 2/3 equals 0, so 2/3 is a root. So now we have p of x equals this factor, and this quadratic factor. See? Here's our constant, here's our x, and here's our x squared. See that? So we got 3x squared minus 12x plus 6. That's our quotient right here. Now, because we have a factor that's a quadratic, we can use the quadratic formula to find the other roots. That's great. All right? So keep in mind, this is our quadratic factor. Okay? So if you remember the quadratic formula, we did this a couple chapters back, and the standard form of a quadratic function, this is written in that, 3x squared plus 12x plus 6, matches the ax squared plus bx plus c. So all we have to do is substitute our values into the quadratic formula. So what we get is x equals a negative of a negative 12. See that? Because it has to be a negative b, and we already have a negative, so we make it a negative of a negative. And it's plus or minus b, this negative 12 squared, minus 4, a is a 3, c is a 6. And then it's divided by 2a, 2 times 3. See? So, all we do is we combine these like terms up here. We can distribute this negative into the parentheses and get a positive 12. And we get a 12 here times a 6. Now, all we have to do is 12 divided by 6, which is a 2. And then negative 12 squared divided by 6 is a negative 2 squared. 12 divided by 6 is 2. See? It's a negative. It's squared. And 12 divided by 6 is 2, and 6 divided by 6 is 1. So really what we get is 2 plus or minus the square root of negative 2 squared minus 2 times 1. Well, we know 2 times 1 is 2. And we know that this, negative 2 times negative 2, is a positive 4. So basically what we've got is a 4 minus 2, which is a 2. We have plus or minus square root of 2. So our other roots are 2 plus the square root of 2 and 2 minus the square root of 2. So our rational roots of p of x are a negative 1 and a 2/3. All right? Because that's what we found out from doing this part. And the irrational roots of p of x are 2 plus square root of 2 and 2 minus square root of 2. So we found 4 roots. We found the rational ones and the irrational ones. And the quadratic formula helped us find that one. All right? Got a little bit more to explain here. Now, this is going to help a lot if we have p of x equals x to the third plus 6x squared plus x plus 6, all of the coefficients are positive values. And when any positive number is substituted in p of x, we get a positive value, never a 0. So no positive number can be a root. We eliminate positive factors for 6 and concentrate on the negative factors. So here's the negative factors of 6 are constant. Okay? Don't even need to worry about the positive ones. All right? So let's try negative 6. This is our polynomial with just coefficients. We have an invisible 1, then a 6, then an invisible 1, and then a 6. All right? And we're going to do synthetic division with the negative 6. So we drop our 1 down. Negative 6 times 1 is negative 6. We add them together, get a 0. Negative 6 times 0 is 0. We add them together, get a 1. Negative 6 times 1 is negative 6. We get a remainder of 0, so it is a root. And here's our quotient. We have a constant of 1. There's no x value, but we have an x squared. So look, we have x squared plus 1 as our quotient. So we know that the factors of p of x are x plus 6 and x squared plus 1. Now this one has no real roots. And the only rational root of p of x is a negative 6. And the other roots are I and negative I. Okay? Our imaginary buddy. All right? So here's a wrap-up of what we've got. I want you to remember that sometimes there may be no rational roots. And on your test or homework, that's what you're going to write. No rational roots. If you don't get a remainder of 0 in the synthetic division, there's no root there, okay? And if you've tried every single one of them and you don't get a remainder of 0, then that one didn't have rational roots. Might have irrational, don't know. If the polynomial doesn't have a constant term, we have to first factor out the greatest power of the variable that we can. So I've been showing you what to do when there's a constant and getting the factor, but what do you do when there's no constant? All we have to do is factor out. Now, because there's no constant term, our constant is equal to a 0. So all the numerators of our factors for the constant term would be a 0. And we can fix this dilemma by factoring out the factor of x. So we've got 5x to the 8th power. So we're going to factor out x and get 5x to the 7th power. See? Because when we distribute back in, we'd get that 5x to the 8th. And that would become x to the 3rd, x to the 2nd, and that would become our constant. See? So by factoring out that x, we've lowered each one of these, and we created a constant. Now we can use the Rational Roots Theorem. Now we can find the factors of 2 and the factors of 5, make those factors our numerator, those factors our denominator, and we'd get a 1 and a 2 and a 1 and a 5, and here's the 1 as a denominator, here's the 5 as a denominator. So our possible roots to use in synthetic division would be positive or negative 1, see? Positive or negative 2, positive or negative 1/5, or positive or negative 2/5. So we have 8 choices, and we find out if the remainders are 0 to prove if they're roots. All right? A lot of information. Long video. I'm sorry. But I wanted you to completely understand the Rational Roots Theorem with the synthetic division and the quadratic formula. All right? Our next video is 11.4b, and we're going to talk about a shortcut we can use with synthetic division when you've got a lot of roots to figure out. Like in this one, we had all of these possible roots. Well, there's an actual shorthand that we can do for synthetic division to make it go a little quicker. It's going to be links to those previous 8 videos. I'm going to add this to the Algebra 2 playlist. And I want you to remember, if you can help me out on Patreon with $1, $5, $2, whatever, I'll really appreciate it. I make all of these videos for free. And I don't run ads in the front. And I really, really need your support to be able to continue affording doing this. I'm a grandma on Social Security fixed income, and I struggle every month to make my bills. So if you can just help with $1, it would help me out. Have a great day. I'll see you next video. Keep trying. Bye.